סרט רץ.
Okay. As hello everyone, my name is Barash from the Computer Science Department. I'm a PhD student, and I'm doing a fellowship under the supervision of Professor Deichmann. And the talk that I'm going to deliver today is about my project and its context of history and philosophy. And the name of this talk is Statistical Proof versus Scientific Theory, and what can AI actually discover in terms of scientific research. So I'm going to start to talk about, present my research, and then we're going to think about the research from the philosophical perspective, and then we have time for suggestions, questions. Right. So in my PhD research, I built a system that can. In my research, I delivered a project that can segment the skin, that can run diagnosis of the skin from images that were taken non-invasively. They were taken non-invasively, meaning that there is, think about, imagine there is some kind of machine like ultrasound that penetrates the skin slightly. And then we want some kind of AI to segment the image. Why do we want it? Because we have a hard limitation on the number of experts we can use to diagnose images. Okay, so this is the goal of the project. This is the high. So using my mind, one project does, and the question we have in my mind, we can start on the second part, is does it know anything? What does it mean to know something statistically? So some technical data. So this is how a non-invasive image of the skin looks like. It's taken by a system called OCT, optical coherence tomography, which penetrates exactly to capture the top part of the skin, called the epidermis. And what we want to do is to segment that. So in this image, if you can see, it's really the top part of the skin. And why do we want that? It turns out that if you can measure the thickness and waviness and geometrical features, you can predict things like atomic dermatitis, psoriasis, because this is when the skin becomes thicker, the epidermis becomes thicker. If a person has diabetes, it becomes thinner. And general abnormal geometry is correlated with skin cancer. So this is what I did. Some previous work. So we divide the timeline to pre-deep learning phase and post. So basically, around 2010, the deep learning revolution started, and basically completed in 2018, approximately around this split. No one is writing manually how the shape of the skin should look like. And before that, it was mainly handcrafted. So in a way, you can think about it like an hypothesis. So the person that writes the formula maybe says, I'm pretty sure that the epidermis looks like a second-order polynomial with this amount of variables, etc. And then he runs this pattern matching over the skin, and with some extra processing techniques, can detect what's happening. And then we have the deep learning phase. Deep learning phase, we don't have such a clear hypothesis. The first work on epidermis was done in 2020, but Rocio de la Mort, but it needs many annotated images. When I'm saying an annotated image, I'm basically saying, find a dermatologist, pay him around minimum $200 an hour, and track down the pixels, the thin pixels here. This is one slide, but each scan generates a 3D image. So you have thousands of slides for each one biopsy of the skin. Okay, so you need thousands of these. This is a blocker. But you need many of those to train an image. 2023 to 2024, you have something that's called foundational models. So basically it's very large models, high compute, a lot of data, generalists. And then some version of them were also trained on medical data. Some medical data is easier to gather than the one I just showed. Millions of images of biopsy are much more available, and it was trained on those highly available regimes. And around this time, a collaborator from Stanford had some technique to convert the non-invasive image to invasive. I will show it in a second. But virtual, so we call it a virtual biopsy. So basically we take an image that is non-invasive, and then we basically prepare for it or map it to something that looks like it was taken invasively. So this was 2024, and my project builds on that, basically to segment that virtual biopsy. Yes, so just want to show really quick how does it look like. So this is real biopsies. This is taken from the body, right, into the. This is the matching OCT of the same skin tissue, and this is what the machine learning model was trained on to convert this thing to something that looks as similar as possible to this thing. So we call that a virtual biopsy. Okay, this is what my project segments. Okay, so we have very nice. I have very nice results, and now we finish the part of how it was done technically and the motivation, and let's talk about where does it stand in terms of the philosophical aspect. We want to know what the model learned, or what is my entire solution. What does it know about the skin? And we will we will use two prisms to tackle that question. One prism will be Popper, who believed that in order to know something in a scientific sense, we need a theory that is refutable, some kind of a brave prediction that you can imagine how it might be refuted with maybe a counterexample. That could be a falsifiable theory, and that would be Popper's standard for scientific knowledge. Bacon, on the other hand, said, first we collect the data, then we rationalize over it. We look at the data and we let the pattern emerge. We try to detect some kind of a generalizable rule that basically jumps out of the data, but the rule normally is the hypothesis that we as humans or the scientists come up with. So this is basically induction. Okay, so we have data, a person that comes up with a theory coming from the data, and then we have a hypothesis that generalizes. If I'm looking at the OCT and the epidermis diagnosis with computers, so before the deep learning era, handcrafted functions, right, polynomials, etc., and manually built pattern recognition functions is Popperian. You can think about it like I believe this is how the skin should look like, approximately, and you can fit a function. Deep learning, on the other hand, what I believe is related to data first. We collect the data, we train a model on this data, and then the model learns to predict good answers on the data we collected, and what we hope is that it generalizes. But there are some caveats here that we need to think about. From the Popperian perspective, what is the hypothesis? What is the brave hypothesis that came in the pre-deep learning era? So maybe it didn't happen this way, but maybe one hypothesis we could project, we could make, is there is enough signal in the non-invasive image in order to detect those biomarkers. And this is a hypothesis that maybe it's quite narrow, right? We proved it in a narrow way because we only proved it for our own small hand-collected data set and verified it with small data. So this could be a narrow hypothesis that could be done from the Popperian perspective. But then when we try the same model on skin samples that has cancer, it failed. The skin looked quite different. It was much more wavy, and it failed. We couldn't segment it. So the normal behavior of people that work in deep learning, okay, so let's collect more data, specifically skin samples with cancer, and train the model on that. But the Popperian perspective says, wait, that means that you had a hypothesis, and that hypothesis was refuted. It was wrong. But the deep learning perspective is that nothing is wrong. We just didn't get enough data. So this is the kind of irrefutable nature of statistical learning. I want to stress that, okay, so science builds falsifiable theories, not general laws. They try to build the theories and improve it one over the other. But my method, basically coming from statistical learning, does neither, not that and not that. It basically finds some kind of statistical regularity in data, and it doesn't claim any kind of generalization. The connection to reality from the statistical perspective, how do we make sure that our model didn't learn something that is absolute garbage? Because it can. So we need some kind of grounding to reality. And the way that I did it, and the way that is very common to do it, is basically ask an expert, is that segmentation, does that answer is correct? Is this really the epidermis? And we can measure it numerically by counting the number of correct pixels that were לכבות את ההקלטה, מה הסיסמה?
זה חלק מהקונשנס.
אם אני זוכר.
memory.
Okay, so now we move from Popper to Bacon. Yes, I wanted to put the years here. So this is quite interesting because it's almost 500 years old. So Bacon was discussing the collect data, rationalize, generalize theme, and he basically said, be careful of four caveats, and described as the four idols. So imagine people living in caves. So this is how this is the idols that were basically causing them to have generalization mistakes. And let's go over each one and apply it to what I did. So the first idol is tribe, so the tribe is mistakes that are common to every human being because they are human. Imagine, think about visual, common visual errors like Fata Morganas, or think about this tendency of people to jump to conclusions even without evidence, or give para-natural explanations to rare events. So this is the kind of idols that tribe makes, kind of errors that tribe makes. So in the AI case, we give it a human nature. We think about it like a human. When we talk with it, some people fall in love with it, some people think this is their best friend, and we apply to it our own human nature. The second one is the cave. So the cave means, think about like this kind of person that lives alone in the cave.
Danny?
Yes, I will finish really. So the individual. So what happens for my own personal background, or the person that comes up with the hypothesis, I didn't have cancerous skin samples in my data set. Right? So I didn't see it, so I don't know it exists, so I assume that my training data represents the world. The marketplace is basically all the people that talk to one another, and then we are limited by language. So basically we are marketing those general foundational models as being able to handle many types of medical images, like the biopsies that I was based on, but they are not. They are not generalized. They don't generalize to skin and to skin cancer and theater, right? The things that are basically are passed to us by tradition and by fate. So we believe in AI. We have this we believe it because of cinema, because of books, because of and because of the general hype, right? So we want to believe that it is something that knows, something that is deep. So to finish my talk, some ideas that I got because of those critical perspectives is that AI is very good in adjusting itself to any kind of truth, but it doesn't know what it doesn't know. So, and this feels like the main limitation in applying it in real-world scenarios. And I have a sub-hypothesis which is quite known. So wherever we didn't train, this is where AI fails, and this is quite a known fact. The generalization error, but the problem is that it doesn't know what it doesn't know. This is still an ongoing research, and it feels like the most important thing to research as the next experiment. To basically say what it doesn't know, to try to train it to say, I never saw this kind of picture before. Yes, that's it. Time for questions.
Yeah.
You can set up. You can set up already.
Maybe
while there are questions.
While the Arunavo sets up. Stay, then. Maybe there is one question. Let's see. Uber? Okay, then we go on. Yes.